for getting me. Okay, so I'll talk about how hydrodynamic emerges from some microscopic description of the system. It's a bit of not very rigorous, but it's a intuitive study. And we see that this derivation also gives you some difficult corrections, and then that will allow us to study crossover from diffusive transport and transport in an 1D system. Okay, so let me start from a more general perspective. Suppose you have an extended system which is connected to two reservoirs at different temperatures, then an energy current starts flowing across the system. For example, if you hold an iron rod against a lamp, then you start feeling warm on the other side of the rod, which means that some amount of heat is getting transported through this rod. And as the current flows, temperature profile also gets established across the system. This side has higher temperature, this side has smaller temperature, lower temperature. So then we have temperature profile that gets established. Now, in a macroscopic system like 3D systems, like iron bar and others, this phenomena can be phenomenologically described in the stationary state by the following law, Fourier's law, which says that the current density in the system is proportional to the local temperature gradient of the system, the temperature profile that gets established. And there is a constant which depends on the material of the system. Yeah.
It is not diagram, I understand, but it is not exactly linear.
Yeah, I think linear. There have been linear in that context I talked about. So this is of course this law says that it has to be linear because in a steady state this current is constant, and this is also constant, so we should get a linear profile. Of course, this law says that this current should decay with system size. As you increase the system size, should the value of the current should decay as 1 over L. And if the temperature profile is small, then this profile should be linear. As you were saying, it has to be linear. Otherwise, if it is not small, then this kappa might depend on temperature. Then, of course, you might have some other non-linear. But that's because of this artifact of the fact that the kappa might depend on temperature. And also in this system, if you consider a small temperature pulse, how does it evolve? We all know that it actually evolves according to the diffusion equation, which is basically another manifestation of energy continuity equation in such systems. But there are systems in low dimensional systems, mainly in 1D and 2D systems. This is not valid, which means that the current does not scale as 1 over n. It scales as 1 over n to the power alpha. Alpha is between 0 to 1, which means that the thermal conductivity, if we define an operational thermal conductivity in the large L limit, it diverges because alpha is between 0 to 1. And such a divergence has been observed recently in 2017. Actually, it has been observed also previously, but this is the most very well controlled and system which is a measurement of thermal conductivity in millimeter long nanotube, which is like almost a macroscopic length nanotube. And they have seen this kappa diverging with some positive exponents.
Nanotube is made of what material?
Sorry?
Nanotube is made of what material?
Okay, so I forgot. I had seen that, but yeah, maybe
Like a normal thing.
but yeah, I forgot. Okay, so apart from that, there are many other signatures. For example, one of the signature is that even for smallest delta t, the temperature profile is not linear, as you are saying. It is not linear, and also it can have singular properties like derivatives of the temperature profile at the boundaries can be diverging. Second, you can consider another situation in which you have an equilibrated system and you create a pulse, heat pulse, and ask how does it evolve. Usually, for systems which obeys Fourier's law, it can be obtained by solving diffusion equation. But in this situation, it is non-diffusive.
These are experimental, not you are showing, right?
These are simulation.
Simulation.
These are simulation, but you have some experiment for this kind of temperature profile, and this was an experiment.
Sorry, what is divergence?
Conductivity.
No, sorry, next slide. It says that the density profile something is divergent.
No, the derivative.
Derivative is divergent.
Derivative of the profile
It has
can
a
be
cost.
divergent.
There's a cost.
No, it is goes to zero as a power.
No, it has a cost.
Goes to zero as a power. This is the only.
No, what about the other side?
This is from 0 to infinity. This side it goes to 1 with the
No,
similarity.
there are also the similar divergences there.
It depends on the system. For example, this is a symmetric system where that's why you get a divergence both ways. But you can have a system in which you can have divergence only at one side. For example, the system that I talked about, it has divergence only at one side. Okay. This divergence is actually related to the thermal conductivity divergence. Everything actually, all of them are related. I try to bring out that later. Yeah, these there are experiments, but it's not so very. At least people have seen signatures of non-diffusive transport, but not very clearly because it's very difficult to actually manipulate heat pulse. Like unlike electron transport, it's very difficult. So there are in 2D systems you will have done by putting laser pulse, creating a heat pulse, and looking at the temperature profiles on the other sides, and they look at how does it, but it's not very conclusive. But there are experiments.
Whatever experiment was counted on these studies are only for heat transfer or also electrical transfer has been done.
So these are energy transfer.
Yeah. So
Not for electrical.
I got that. But is there any sense to this question of asking that electrical transfer will also focus on anomalous properties?
No. Electron transport is generally, I mean, you don't look at electron transport in such 1D microscopic system in ground system. They are very minute, where you don't talk about such things, or you can do only linear response theory. And you don't ask system size theory. How do you ask system size? I mean, the transport through these wires are only.
Yeah.
Unless, yeah.
We had that. So is there? So I don't even talk about that. So what is is there an underlying particle or anything that is making this kind of anomalous flow?
Yeah, there could be. There are some theoretical models, but I don't want to win that thing.
Okay.
Maybe again, at the end I can make some comments on, on such. Yeah. Okay. And another signature is that I mean, if you can prepare a system with half at some temperature and another half at another temperature, and see how does this step temperature profile evolve. And systems in which you have normal transport, like which obeys Fourier's law, this evolution can also be obtained by solving diffusion equation. But here, systems which shows anomalous transport, you cannot get that evolution from solving the diffusion equation. You need to have some other equation. Question is what needs to be that equation. A few years back, actually, I had given another talk here. It's mainly on this point, the particular equation that will replace the diffusion equation. And the last characteristics is that the current correlation in equilibrium actually has a power law decay with time, and that actually is the main signature which actually causes many of this behavior. But these are also independently observed. Okay, so these are main signatures of anomalous transfer among many others. But there is no general framework to study this anomalous transfer in varied systems, and that's why it is crucial to study specific microscopic model systems to understand these features of anomalous transport. But recently there is a development which goes under the name nonlinear fluctuating hydrodynamics, which explains many features of this anomalous transport in a wide class of systems. And this theory developed over last 10 years, 10 to 15 years, started from this paper by Uttam Narayan and Siram Ramaswamy in 2006. They did some more couple calculations, and then in 2012, Bangalore wrote an paper in parallel, and after that, or what actually generalized you can wrote it in full generality. So let me briefly talk about this. So what he considers is that you have a system like this, where you can write down the Hamilton in terms of some local terms. These are, you can think of these as lattice systems where you have particles in each lattice side, and these are momenta, and they are the interactions with the nearest neighbor. These are the positions, and this is the separation between the particles. In such systems, you have three kinds of quantities: total stretch. This is not L, this would be R. Or maybe you can think of this as A. That's a total stretch, total momentum, and total energy. And corresponding to that, if you do a post-scaling, you get some continuity equations. And as the system evolves, you can see that these quantities are evolving. And the idea is that this dynamics is complex enough so that it actually takes the system to a thermal equilibrium. And you assume that you assume such picture that you have a thermal equilibrium locally, which is it is called as local thermal equilibrium. At different positions, you have some local equilibrium, and this local equilibrium at different positions are in space it varies very slowly. You can assume such picture, and since it is varying in space very slowly, it actually also evolves very slowly. And why? These local thermal equilibriums are actually described by local temperature, pressure, and whatever other conjugate fields corresponding to this. And these conjugate fields actually determine the corresponding values of those fields locally. And since those values are actually connected by the time evolution of these are related to the space derivative of those values. So if they varies very slowly over space, they also evolve very slowly because of this continuity equation. So what you do is basically this is a prescription. So in local thermal equilibrium, you actually replace this current by average currents in the leading order, average in the local equilibrium state. And once you write down this current in the local equilibrium state in the average in the local equilibrium state, those currents will be functions of the local temperature, pressure, and other conserved quantities, basically in general chemical potentials. And by local equation of state, those chemical potentials can be expressed in terms of the local values of the field itself. And that's why these currents will be functions of the local values of the field itself. And as a result, these equations become autonomous in the fields. And this is the kind of a basic notion of hydrodynamics. These are dependent only on the fields itself, not any other quantities. Okay, so this is in the dominating order. But I mean, of course, you want to add dissipation and fluctuation, add fluctuations. But you cannot just add fluctuations because you want that the thermal equilibrium to maintain. You also have to add dissipation. You can add dissipation. This is the simplest kind of dissipation that you can add, and the noise. And you have to add these two terms, phenomenologically obey fluctuation dissipation relation. But of course, these terms actually, I'll make a comment after 2 slides. They appear because of the post-grading procedure.
Yes. Delta is inside the dissipation.
No.
Dissipation highlighted. Delta.
No, this is the target. This is the target.
D should be outside.
No, this is del x square. Oh, you are saying yeah, this is this D. I am assuming that this D.
It can be inside. Depends on the microscopic of the model.
Yeah, it can be also, but I'm saying this D does not depend on X.
No, it cannot be inside.
Why it can be spatially dependent?
No, but you are considering spatially dependent.
No, this D is independent of.
If D is what you don't have any control. If it comes out of course grain.
Yeah, but I'm saying here you take this D to be constant because this D is related to the fluctuation, and that fluctuations are global fluctuations of global equilibrium, which is homogeneous.
But in general, it can depend on U itself.
Right.
So that's why this should be in principle outside.
It can depend on the U itself.
So that's why this should be in principle outside.
I mean, the general form is del x D del x E.
But it's a Fourier law, right? And the diffusing current should be D times gradient. So this should be outside. Okay, fine.
Okay. 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 So the next step in a non-equilibrium fluctuating in hydrodynamics is basically these expressions of the currents a bit complicated. So what you can do, the simplest you can do is basically expand this in the leading order, which is linear order, and without the dissipation and noise term, you get these Euler equations. So in these Euler equations, the U's are what? U's are basically the deviation from the global equilibrium value. So that means any excitations in this equation says that any excitations actually propagate ballistic, right? Because this is a constant matrix. It's like a del tu equal to some a del x u. This if you diagonalize, it will give you some velocities. So there will be some balancing propagation.
So, sorry for the interruption again. I think it's a phenomenological equation, right? Or we are going to derive it later.
I make some comments on this. So I'm saying these I am describing this theory, how it is described. Okay. Now, if you add dissipation and noise, so this ballistically the ballistic propagation, in addition to the ballistic propagation, you have diffusive spreading of the excitation. The clear excitation they move ballistically, but because of these terms, they also spread. For example, if you clear excitation, it actually in this equation it gets split into three delta functions. I'm assuming three concepts, three delta functions. And because of the symmetry of the problem, of course you will have one velocity, otherwise you will not have spatial inversion symmetry. So the two boards will move in the opposite direction and one board will not move. And because of so one delta function will get split into three delta functions. But as you apply this, add these two terms, they will also start spreading. Now, the next term that you can add is the nonlinear term, which is the nonlinear order deviation, expanding this to second order. And because of that, it can actually change the whole behavior. You can have ballistic propagation is there, but you can have the possibility of non-diffusive spreading. This term might give you a dominant contribution to the mode propagation or mode evolution than these terms. Okay, right? There is a possibility, and that kind of possibility gives you the superficial transfer. Okay, so this theory is pretty successful in describing space-time density correlations in the systems and the corresponding current space-time correlations, and it gives power, general power law of behavior, and that actually gives rise to this system size scaling of the current and the exponent, and this theory is pretty general. We can apply it to a general class of Hamiltonians, and it actually gives allows you to classify different Hamiltonians depending on the value of the alpha, which characterizes the transport behavior. Very good. But the question is it possible to derive or establish these hydrodynamic equations in an alternate way by starting from microscopic density, which you are asking, with, especially these terms and these terms. These terms are not very difficult to derive, but these terms. Is it possible to derive? Question is it possible to derive the diffusion and noise terms as well? So there are very few attempts. One attempt, this is a most general attempt, is actually they did very recently for Hamiltonian systems on a lattice, and they established this form, but their expression for the diffusion constants are not explicit in terms of the Green formula of the total current in which you subtract the group part and the sorry, I made a mistake. So yeah, and the linear and the non-linear part. All these parts are subtracted, and what remains actually you have to subtract in such a way that what remains, if you consider the correlation, that correlation decreases exponentially, and that can give you a diffusion term. Okay, because any transport coefficient will be formula is a current correlation integration. Now, if the current correlation has, if you want to have a diffusion constant, which is finite, this current correlation should decay exponentially. Otherwise, it cannot have a integral to finite. Right? If it decreases formula, then it will diverge. So that means you have to subtract this part, and that actually appears. I'll also try to demonstrate in my calculation how such subtraction appears. Not exactly in this setting, but in another context. Another model in which this question was studied, addressed, is this three-particle collision ideal gas. So this is an ideal gas of particles, up to point particles, but the undergo stochastic collisions. So you choose any three consecutive particles at random, and then mix their momentum in such a way that if the total momentum and total energy is fixed. So in that model also you can actually find out establish the hydrodynamic equation and the diffusion of the noise terms very rigorously. So these are some few general comments. Is that although the diffusion and noise terms you have to add into the formalism, but it doesn't actually affect the leading anomalous behavior. It actually allows you to write down the it actually makes this assumption that there is a local equilibrium picture which evolves. You cannot make those assumptions unless those terms are there. But their values do not actually affect any of the anomalous behavior that you observe in the living. Okay, so that's why that presence is important. How much are the values, the diffusion term and the noise strength, those are not very important. Okay, very good. But since they are there, and if you know the values, then you can actually try to study a diffusion anomalous term, anomalous crossover. For example, if those nonlinear terms are not there, then you have a diffusive transfer.
But non-linear terms in the mode coupling.
Mode coupling terms. Now the mode coupling terms contribute at a longer length scale. That means if you start a system which is smaller length scale, then that means even though those terms are there in your theory, they will not give you reduced contribution. Diffusion terms will give you reduced contribution. That means as you increase the system size, first you start seeing diffusive transfer and then you start seeing anomalous transfer. And that's how you can expect a crossover, even in a nonlinear transmitted hydrodynamic scale. Is it clear?
It depends on how strong the mode coupling is compared to the size of D.
Yes, of course, it will depend, but that will give you a crossover length scale. All these comparative strengths will give you a length scale. And I will demonstrate. But once all these terms are fixed, strengths are fixed, there will be a length scale. And if you start your system size smaller, then you start seeing diffusive transfer. And then as you go over this length scale, you start seeing anomalous transfer.
So instead of changing the length of the system, you can also vary one of the other parameters and see the same.
Yeah.
But it may be difficult to vary the other parameters because you have any direct control.
Okay, so anyway, I'll demonstrate in my model. Okay.
What is the scaling limit you are talking about? If I say that housing scale, position, and space, as that we see the diffusive cost for diffusive output.
I have to slide for that. Very clear. Either I keep the answer right now or
No time.
okay, so maybe briefly I tell you about this problem. This is not the main part of the talk. So this problem is we have hard particle point particles, and even though they are looking like big, but they're point particles, they are of same mass, ideal gas. So in between collisions, they just move according to Newton's law, realistic. But once at some rate, you choose any three consecutive particles and mix their momentum such that this is the momentum before collision, this is the momentum after collision, so that the total momentum remains same and the total energy remains same. That is the dynamics. And you add touch baths. I'm not going into the details how we can model the bath, but you can just think of the linear particle polarized. It comes out with a velocity that is chosen from some Maxwell distribution at some temperature. Not exactly Maxwell, but it's a one-sided Maxwell. It's called Maxwell bar. Okay, so for these systems, if you want to follow nonlinear fluctuating hydrodynamics, NFHD, then you would write such an equation like this. Okay, these are the equations that you would write from the philologically, and you would add a diffusion and noise terms. I'm not saying why these terms are not there. You can argue it, but it turns out that we can actually start from a microscopic description and we can derive these two terms. and we find that this the diffusion term is actually explicitly expressed in terms of the density, temperature, and the stochastic collision rate. And the sigma is basically, of course, related to the d by fluctuation dissipation. It is given by this. And one can show that this noise is also Gaussian, and it's by Gaussian model. You can show that. So you can establish for this model. And since we know this diffusion and noise term, diffusion term very explicitly, then we can compute the current, and current will have a leading term which is anomalous, which is e to the minus 2/3, and a normal part which is all over L. This is the Fourier part. If this term was not there, then it would have been the dominating term. But this is the dominating term because the actual dominating transport mechanism is anomalous. So you have I add this correction also, and if you write down, so these terms explicitly, basically this is the Fourier term and this is the anomalous part. If you add this, you can write down this for current in this form: normal part times 1 plus L by LC. LC is the crossover length. Yes.
I think you are doing it from the microscopic, but if I now try to relate it to the nonlinear fluctuating hydrodynamic language, then this anomalous what you said, that is coming from the most of the part, is that right? But then it is L to the minus 2/3, and the diffusive part is L inverse. So for all L, this anomalous term will dominate. No?
Oh, that's what I'm trying to demonstrate.
No, but you said that there could be a length scale below which diffusive part.
That's what I'm trying to say. I said these scales is all over L. There are factors. These scales are factors. These are exactly these factors. And if I write it in this form, you can see that this is normal plus 1 plus L by LC to the 1/3. Of course, at very, very large L, this term is dominating. And that will give you, this is 1 over L, this is L to the 1/3, it will give you a minus 2. But if you take L to be much smaller than LC, assuming that LC, even at L smaller than LC, you can actually have a hydrodynamic distribution. That means you have to choose your parameters such that LC is already very large, so that even below LC you have a hydrodynamic distribution, so that you see the basic structure, and then you cross, and then you go to anomalous. So this is the and LC is actually dependent on the system parameters. Here it depends on the collision because that's the interaction state.
No, on the initial assumption, or you really show from
Which one?
this LC. I mean,
No,
that-
this I just write.
The hydrodynamic exists.
No, hydrodynamic exists, you have to assume. And then you calculate. And then you, if you want to do it microscopically, then you have to choose your parameters such that LC is large enough so that you can apply your hydrodynamics even before LC. But that's kind of assumption.
So no, that's a confusing phenomenon. Hydrodynamics is always large scale.
Yeah,
So, LC, I think it has to do with some correlation length in the system, right?
no,
LC, I mean,
no,
that's
that's a crossover length.
possible length, but it must be related to the microscopic dynamics, and it must be the correlation length. What is the other length scale? I mean, why you think that there should be another length scale LC other than correlation length?
No, it's just that the two competing terms. So, for example, suppose in the mode graphing,
From the microscopic, other than the correlation length, how this LC will emerge? You see,
why can't it other another let's say
no, it might be microscopic. LC is just a lattice spacing or say mean particle.
Oh, this is the expression for LC, right? Depends on the density and
So this is mean particle. So,
No, it's actually
Physically
okay,
what?
for this model.
Physically
For
it
this
is
model,
what?
this is actually you can for this particular model you can have an interpolation. This length scale is actually few orders of mean free path.
Right. That's basic.
Let's say 10 or 100 orders of mean free path. This is so that only over such a length scale you see diffusion.
Right. So,
But if you have very large system size, when your system size is few orders of mean free path, you can only have diffusion because your hydrodynamic modes doesn't get developed. But diffusive transport is also a kind of a hydrodynamic destination.
no. But LC is really mean free path. So then I would say it's a microscopic scale. So at the microscopic scale, I mean, how do you then think that the hydrodynamics will exist, or you can even talk about hydrodynamics. That doesn't
I
make
don't
sense.
understand if you have a random walkers on that.
No, random walker is an interactive, non-interactive particle system.
Yeah, but density
If
of
you say
random walkers
can you, if you take two particles, can you talk about hydrodynamics?
no. But I don't have two
I mean, we
particles.
cannot.
I don't have two particles. I have many particles.
No, many particles, but the length scale must be that is a microscopic length scale.
Yeah, but it's actually much larger. This
But it
length
also
scale.
depends on the density, but not exactly.
No,
the
density
It's
is
not
a mean
exactly-
three-part, it's a mean three-part.
No, it's not exactly mean three particles.
Yeah.
Yeah.
Mean three part can also be.
No, how? In one dimensional system, how mean three-part can be much larger than density 1 by rho? It cannot be.
No,
I
I'm
mean,
saying
from the conservation law, it cannot be.
it's not exactly mean three particles.
No,
100 times, 1,000 times mean three particles.
physically, it has to be either the microscopic length scale
No.
or the correlation length that is
No, but
different.
then give me some arguments why. Why can't there be another length scale? Because
No,
I
another
have
length scale, no, I mean
I
another
just see two currents, two terms, and both are dimension of currents, and you have a one length by something, and I can define a length scale definitely. I can
No,
define
you have
absolutely
designed the
define a
length
length
scale
scale,
and if
and that I don't see this length scale appearing in the correlation. Just that what I'm trying to say is that okay, you can.
no, it must appear in the correlation length. Otherwise, dimensionally, I mean, it doesn't fall. Dimensionally, it must appear.
Why?
I mean, dimensionally,
Maybe I
dimensionally can you
follow the-
construct another length scale? And if you cannot construct, this is the only length, and that is a microscopic length.
No,
That's
but
right.
you can have many.
No, for example, you have put up a temperature gradient in the system.
Hmm.
There's a length scale associated with it.
No, but no, that is there. But he's talking about, I mean, when L is inside itself of that length scale. But physically, what is the LC? That is another length scale. I agree. But apart from that length scale, it has to be only microscopic length scale, dimensional. Or some diverging length scale. That is a many body effect.
No, but I'm trying to say that in these systems, if you look at the density correlations or the
Right.
current correlations, those usually have all of behavior. You do not have.
So then diverging length scale.
Yeah, you do not
Okay, so
have.
then this is a microscopic length.
You do
And we
not have.
cannot talk about hydrodynamic length.
But
No, but suppose you have microscopic length scale, some L1 and 1000 L1, they're not of the same order, right? It's still same dimension. But
What is 1000 K? Maybe we talk later. I think. Yeah.
no,
I
also length scale,
No,
right?
you understand my point. I'm
no,
saying
but okay, let
no,
me.
you have this room, and you have only 3 particles. So now 3
I
particles.
understand three particles for three particles cannot do
No,
hydrodynamics.
but you are talking that.
No, this is not a microscopic length. That's what I'm saying. Even
No, but you
this.
said exactly that.
No, I said this is a.
Deriving it from the microscope.
No, but physically it has some meaning. Right? It has to be mean 3 parts. Otherwise, what?
No, but now you are saying it is a mean because then you are trying to argue that okay, since it is a mean because we have agreed, then you cannot do hydrodynamics. But I'm saying this is much larger than microscopic length scale. So over that length scale also you can actually, unless you cannot do hydrodynamics. It has to be very large. If you do not have, if this is not very large,
No, but
if
expression
this is not very large, you won't see this
No, the
crossover.
expression you have written is not large. It's finite. I can see it is finite. How it can be large?
No, but this rho 0 are
No, but I'm saying
parameters, right?
this is much smaller than 1 over, much larger than 1 over rho naught. That's what I'm trying to say. If you do not have that, if you do not choose such parameters, then you won't see this crossover. Because below this, you cannot apply aerodynamics and you don't get this truth. Because we are microscopic. This is those two terms, assuming that just there is a length scale LC. Just below that, you also have hydrodynamic description. Just above that, you also have hydrodynamic description. That's what I'm trying to say. But L going to zero limit is a microscopic description. Why you don't expect this to be valid? Okay.
No, then you are claiming that LC is large. I mean, this I don't see.
Okay. Another way of
I mean,
saying,
rho naught is
another way
finite.
this LC might appear is this. So in the mode coupling, suppose you start with this aerodynamic equation. What is this? This aerodynamic equation, and if you do mode coupling, in the Fourier mode, this in the leading order you will have e to the power minus something k to the power nu t, right? K mod k to the nu t. But the next correction is exponential minus b k square t. Now, if you write down this in terms of take common, and you write down, you can write it as k to the power nu plus k by k c to the power. In that way, you also have a k star. That k star is exactly same as this L star. I mean, this is the same as this thing. So you have a diffusive propagator and you have this propagator. Now, which one is dominating? Depending on at which k you are looking at. But these forms comes from either underlying assumption that you have an hydrodynamic base station. Otherwise, you cannot write these forms. So that means you can write these forms assuming that there is a k star in which on such scale of k star you can scale to hydrodynamics. That's what I'm trying to say.
What is the new norm?
No, nu naught was the stochastic
Strength.
Data,
stochastic
data
condition.
fixing.
Time, then if you want.
Yeah, I'll okay.
Okay,
Let me go to the next model, which is more detailed, and there also you'll see such a crossover, and there I'll come to this point in detail. But anyway, this is a demonstration of this crossover numerically, where I just plot these two functions for the same function but in a different way. U is the log of L by LC, and you see that the data for different parameters actually fall. Actually, it's very this side is anomalous and it's very difficult to actually get. For one set of parameters, the whole curve, it's very difficult. So we do it for different and different things give you different LC. And different, you see that even for very small LC, you can actually follow the diffusive curve. But to get it on the other side, you need a LC to be, you cannot get LC, which is very small. Then you won't see this diffusive part. Okay, or if you want to see the diffusive part and the anomalous part, then you need LC very large, but then you cannot do very large system simulation. It's very difficult. But that's why we did it in this way, and we can demonstrate the crossover.
That's the question. Three-point position is defined. So can there be systems where mu is like actually completely absent, and the system is completely diffusive for any length?
No, but if mu is not there,
LC
this thing is also then be completely non-interactive.
So you are saying the
Completely
moment you have
non-interactive.
interaction, you cannot
And then
avoid.
we know diffusion also it is
Yeah.
realistic.
Okay. So you are
In
saying
such model, you need mu to make both terms new, the diffusion term as well as those anomalous terms to be appear. To appear, you need mu. Otherwise, because you see that the d also depends on mu.
right. So you are saying the moment you have interaction, you cannot get rid of it. There will be a LC.
If you do not have this,
Interaction, you won't even have
Yeah.
diffusion.
Exactly. Yeah.
yeah,
You have nothing. Okay, I get it.
because these particles are non-interactive, they just don't see each other. They just hit and go this
No, I
side.
get it.
So that is the process.
And you also suggested that there is an exponent alpha, like a both are number. What takes up?
Alpha is this minus 2/3.
Right, but who is what is taking that number?
Oh, that's the mode coupling theory. Coupling theory gives you this. That comes from the structure of the theory, structure of this H matrices. I didn't go into
That's okay. It's just that I'm not very familiar with
Yeah.
that.
No, but once you write it in this form, these matrices, you can write it the whole thing in this form, and these matrices have some properties. And depending on those properties of these matrices, actually, it is okay. Okay, so this gives you some crossover. I just wanted to remind this behavior, this work, but this is the main thing that I wanted to talk about. So such a crossover can also be observed in a simpler system, where you have only two conserved quantities. The previous system had three conserved quantities, and in this case, this anomalous transport usually suggests that you have a super-diffusion. If you consider a localized state pulse, it will have super-diffusion. So in this model, I'll derive a super-diffusion equation for energy pulse. Okay. So how can one establish the super-diffusive evolution with a diffusive correction? So let me explain the model first. So you have a lattice, or each lattice state has some variable eta, which we call volume, and the dynamics is this: V is the on-site potential, and I consider harmonic potential. So at each side you have a harmonic potential, and this variable is in that harmonic potential, and the dynamics is this: eta I dot is equal to eta V prime eta I plus 1 minus z prime eta I minus 1. You see that there is already an asymmetry in the space. So that's why you will not see both sides diverging from the symmetric temperature profile. And also you see only one mode which is moving degree. Okay, and then you have exchange. At some rate, you choose any two successive sites and exchange their eta variables with some rate gamma. Okay, that's the dynamics. Now this dynamics has two concept quantities: the total this thing eta I and total v of eta I. These are the two concept quantities. And the structure of this concept, these are some of our local quantities. And you see the correspondingly you have a local conservation equations. This is already in that form. This is also you can write in this form. More explicitly you can write in this form. So I define a local volume as hi, which is same as eta I, and local energy is v of eta I, which is this. Hat variables are like stochastic variables, and this eta vector is all the configuration. And you can write down this stochastic conservation equations, or the energies you can write explicitly here. You can see that the volume variable current is linear in H, whereas the energy current is non-linear in H. So this is the notation. Hat variables are stochastic variable, which is written in terms of O0. O0 is a global equilibrium value, I think, and the tilde variables are deviation from the global equilibrium value. So hat means this is the stochastic this representation of the deviation, and this is the average value. So average deviation from the global equilibrium value. Right? This notation is clear. Okay, so now what I want to do, I start with the Fokker-Planck equation, which is this from where you have a Liouville part and exchange part. And this is the Liouville part that you can easily see, right? And the exchange part is just that you have there is a gamma here. I forgot the gamma times the, and this vector is represents the configuration after exchanging eta variables at an I and I plus 1. So that means you have this, but eta I plus 1 is the same set of variables. Only thing is that I and I plus 1 are exchanged. Okay, clear? Okay, so this is the Fokker-Planck equation, and it has been proved for this dynamics very rigorously that there is no path, I mean anything. You can take this system to be on a ring, and it can be, it has been proved that this dynamics is very has very good algorithmic properties. It actually takes the system to thermal equilibrium, which can be described by this canonical distribution. Okay, or these parameters can be related to the total energy per particle, because we start with some configuration of this conserve the total, this quantity is conserved, this quantity is conserved. So this quantity is always same as the initial value. So initially it was H0, initially it was E0. So E0 and H0 will determine beta naught and tau. Okay, because the equivalent. Okay, so these are the basically the equation of state. Okay, this is like pressure, this is volume, this is like energy, temperature, and this is the mechanical part of the energy. Okay, and this is the fluctuation part of the energy. Okay, very good. Now, once you have a system which has a global equilibrium, and you have a so that the dynamics actually takes the system to a global equilibrium. Very good. On the other hand, you have conserved quantities which are of this form. You have these local conserved quantities are in this form, where you can write the conserved quantities as some of local terms, and they have the local continuity equation where you have currents which involve only local variables. If you have such a structure, then you generally expect that there will be a hierarchical description. So let me tell you a concrete scenario where you can actually keep that picture in mind to understand it. So the scenario is this: suppose you have, I said that it actually goes to an equilibrium, E0 and H0, and consider a situation in which you have a small deviation around this, which is this in this form for the energy field and the H field, small deviation, and this deviation is over some length scale which is much larger than the microscopic length scale. And as the system evolves, this quantity will also evolve, and the variation of these fields actually sets up a length scale, which is over which you want to write down a thermodynamic description. That's the length scale that I want to over which I want to write, and that hydrodynamic description will give you my behavior on a much microscopic length, which is of the order of system size.
The time dependent length that you are talking
No, you can just set a length scale.
about. You started with some. Then it spreads. So the length scale of variation changes with time.
Length scale of variation changes with time, but I'm saying you can take any one of them in that form, in that order, which is much larger than the microscopic. Then, as the factor with of the length scale might change with time. So that means the derivative becomes more and more. I mean, it becomes smaller and smaller, becomes more and more flat. But the length scale over which this derivative is actually this variation is happening is actually much larger than this time scale. So the factor has this length scale. That factor becomes larger. You can think of it that way, and that factor actually has a hierarchy description. That's what I.
So is it a product measure or it's a non-trivial correlation?
So the equilibrium has product.
Product measure. So there is no correlation.
Global equilibrium doesn't have. Some correlation. Okay. Okay. So keep that concrete picture in mind. So you have this. Now we are considering a revolution at a time scale which is much larger than the microscopic time scale, which is governed by the K naught. You remember K naught was K naught was what? K naught was the strength of the harmonic, which you can think of. You can have K naught eta I plus 1 minus K naught eta I minus 1. So that's K naught. Okay, so and gamma inverse was the time scale over which the exchange happens. So for such time scale, you can write down a Fokker-Planck equation. Sorry, I want to write a solution for the Fokker-Planck equation on a time scale, and I assume such a solution that the solution can be written as a local equilibrium solution plus a deviation from the local equilibrium solution. I make such an assumption. Okay, based on the fact that I'm expecting an evolution of this form which will evolve slowly based on this fact. So that means the behavior over at such length scale can be described by an equilibrium type description with some parameters, but they are different from global parameters, but they are evolving with time. Okay, that's the picture, and the deviation from it. So once I assume this of course locally, if I apply like global this equilibrium state, then I'll have this equation of state. These are local equation of state. Now the deviation, if I write down this, if I put this solution into the Fokker-Planck equation, where is the Fokker-Planck equation? Here, then I can write down the equation for the deviation. The equation for the deviation is basically del delta Pt and L, and then with this local equilibrium term acting on it, and the time derivative of the local equilibrium distribution. Okay, simple calculation. And one can write down a formal solution of this equation. You can write down a formal equation. Basically, you just evolve with this e to the power L t operator of the inhomogeneous term. This term is known because I have made an assumption of the form of PLE. Okay, this is the form of the PLE which depends on eta I. Okay, this depends on the microstate. This is the microstate, and this L acts on the microstates eta. And this is the time derivative of this time. These parameters are time dependent. So I have an explicit expression of this inhomogeneous term. So I have an homogeneous term. I just evolve. So this is the solution. Okay. And
Full configuration.
yeah. Full configuration. This is the distribution of the configuration term. Now you can write down these quantities explicitly, and you can show that these quantities can be written as some these are the nabla is derivative. So nabla beta is the derivative, discrete derivative. Okay, so these times are current, and also these times are current, and this becomes a del del beta I and beta naught del del t tau I, and times some currents. One thing to remember, beta is beta naught plus some tilde. All these things are global variable plus tilde variables. Y is some current. I mean, if you do this calculation, you can write it in this form. That's what I'm saying. L operator acting on this, you can write it in this form. Where I have taken this factor out, you can write it in this form. You have some currents.
What is phi?
No, I'm saying I'm writing this quantity. This inhomogeneous term is exactly this term. So I have divided by PLE and multiplied by PLE, and I'm writing this terms phi, this part phi, this part phi L. Okay. straightforward calculation. But the main part is that this can be written in this drive times the current. Drive times the current. The gradient of the drive, gradient of the field is the drive. It's in that form. And this part is time derivative of the field times the current time derivative of the field.
Till now it is exact.
Yeah?
Till now it is exact.
I mean, this assumption is not exact. This I have made an assumption.
No, given the assumption, the rest.
But this assumption may not be valid always. So you have to condition that what should be okay. I come to that. Okay, so these are the expressions of the currents. These are similar to the original current, except these are minuses because these operators are self-adjoint, but these operators are not. Because these are the Levy operator. These are coming from the axial operator. Okay, anyway.
So what is it?
H was the volume, you know. H was eta. H is eta. HI is eta I, and EI is eta I, K naught eta I square. Okay. So this is the answer to your question that I have made an assumption that the solution is in this form, and I have put these two fields by hand.
How is it called the assumption? I mean, whether it's a perturbation, I mean, it's that small.
Yeah, but who said that I can write the solution in this form? It may not be that always you cannot even write the
Local equilibrium does not exist. That is the point.
Yeah, it may not be. Not for all for
No, right. So
equation.
you are saying that the assumption of local equilibrium is there. Otherwise,
Yeah.
it's fine.
Yeah.
And you have not probably independently checked the assumption of local equilibrium.
Yes.
Am I correct?
Okay. Yes. Now I'm saying if I want this to be a solution, then these quantities should not independently arbitrarily evolve. This should also evolve in such a way that this remains a solution of the quadratic equation. So that means if I demand that this has to satisfy the quadratic equation, it will give you some particular evolutions of these fields. So that evolutions of these fields. Now, if I use the local equilibrium state, this will give you evolutions of the local variables, and that it can give me autonomous equations for the fields, which will give me harmonic. That's the basic plan. Okay, so this is more in the form of equations. So I start from the continuity equations. I write down the average values. I find out the average of these currents in this state. So these averages can be written in terms of the beta and tau I. That will give me equation for beta and tau, but I can use local equilibrium state and express beta and tau I in terms of HI and EI, and that will give me equations. Now I have to assume small derivations, of course, and do linear response, and then I will get evolution equation for the HI and EI. That will give me the argument. That's the basic plan, and the assumptions I think are hopefully clear. Okay, so now I will do this. So first I will assume that this term is just PLE, not the I don't take the this term. So in this state, if I take the averages, of course these currents will be only linear, because PLE cannot generate this. Now if I put that and the linear order, because I am considering only the linear order terms, higher order terms will not contribute to this. In the whole thing, I am considering only linear order hierarchies.
So what is the first time? It's just a Gaussian.
This is the if you have a system which has a non-zero pressure, so if you have a current, so it can these are basically the
Constant current part.
constant part. Do not have
Gaussian.
these are not there, but I just for completeness I have kept it. So
No, just a moment. Second term is the
second term is coming from
non-linear.
no linear part. It's linear. Because I'm writing these quantities in the linear order in derivations.
This
And
comes
what-
from the harmonic.
No, we have an expression for this. I'm just evaluating this quantity in this state. And you get this term. These are not hat. These are day.
No, I mean, this is exact or you have know the higher order term.
I have ignored the hierarchy.
Okay, so it's not equal.
Actually, this one is exact, but this one I have ignored. This is exact, but this one in this expression I have ignored.
But second one is non-linear already.
No, it's still linear.
So H not multiplied.
H naught is a constant.
Oh, H not is a constant.
H naught
Oh,
is
it's
constant.
fine.
H naught is constant, no. And here also I have linearized the equation of state. You do not have tau I squared term. Okay, so recall that you have a term like this, but if you find out this quantity in this state, you'll have this term, linear term, but this was non-linear term. Now, if I apply, because if you take the other one, it will be h tilde square, which I don't want. I want a linearized hydrodynamics. Now, if you use that, you'll get this kind of hydrodynamic equations, which is linear. These are derivatives, and this is discrete Laplacian. So this is Laplacian, this is Nabla derivative. And equivalently, I can write down this equation in terms of tau I and beta I, and these equations become very simple. But these will give you diffusive transport. But I know that from previous studies, there are others. I also have a paper, and there are other studies that this model, the transport is not diffusive. Okay, so how do we correct for that? So then, what I do next order term is I add this correction term, deviation, and if I add this, since this is sum, so I'll have the local equilibrium term plus this part, and this is already in the form of a current correlation, because these were remembered for some these times currents.
So how to, I mean, you have one gradient term and one non-gradient term, J.
Well, this is
J, the first line.
This is diffusive, no?
No, first line, top.
Yeah, but this will give you velocity.
Right, so then it is the diffusive. It's a deep velocity is there.
Yeah, I'm saying it will give you diffusive transport for the energy. This will give you diffusive transport for the energy. You'll have a ballistic mode and a diffusive, but I'm saying it will have a deep diffusion.
Right.
It will not have any anomalous thing. That's what I'm saying.
No, but still it's a drip diffusion. It's not strictly diffusion.
Yeah, in that sense, yeah, yeah. I'm saying
Right. That is
The diffusion you said, because if you have a partition, how does it decay? It decays diffusively.
no,
That
but there
is
is
why
a deep term.
no. How does it spread? If you do not have this term, if you do not have this term, if you do not have this term, if you create a partition, it will just move.
Ballistic mode is there. So then I think that
No,
relaxation length
the ballistic mode makes sure that it moves around the goes. It just moves, it is moving.
right.
That is ballistic mode. But then if you are on the co-moving frame, how does it spread? That is given by diffusion
No, that
in
is fine.
absence of any
No,
other.
that is fine. But it's no, that's fine. The deep diffusion is there.
Okay. Okay. If you write down these things, you'll have a current, and then this term, and these are in this form, gradient of beta, and this, and the currents. So it will have a current correlation terms, and this will have this derivative. Now this subscript I have written because this term came from the local equilibrium distribution. So now what is these derivatives? These derivatives I have already obtained from the previous approximation. So I'll just put those there, and if I put those and simplify, I'll see that if I put those, I'll see that this full term becomes in this form. Interesting fact is that you have only the nonlinear in deviation terms. There is no linear convective term. All the linear convective terms are got cancelled, and all the I mean even if there is these group terms, they are anyway not contributing, because anyway I'll put a gradient of this currents, so they will not come. Okay, so these terms are not. So I'm saying that linear convective terms. What do I mean by that? Uh, this kind of terms. These are linear convective terms which will generate a velocity. Such terms are not there. There are linear terms, but they are in the gradient form. They will not generate velocity. They will generate diffusion type terms, because this is already in gradient. If the current is in the gradient, then dx of j will be a derivative of the second derivative of the field. Okay, so they will not generate a ballistic term. I mean, how do I say the drift velocity term? So either it's a gradient type or a nonlinear in deviations. All the convective type terms got cancelled by this. Now this is in this form. Now I want a correlation of this with this. If you write down these correlations, now what do I? One thing I did not mention is that this correlation was evaluated at local equilibrium, because PD was, if you remember, PD was PD was here with PLE. So that means this was an average with respect to PLE. But really these currents are already in the form of deviations. Already in the form of deviations. So PLE, I can write PGE plus deviations. So I don't need those because those will be higher order in deviation. So this correlation I can replace by global equilibrium averages. So it's basically a correlation in global equilibrium, and the deviations are already there in those terms. Okay. Clear? So this is an important fact that it becomes only nonlinear in or in gradient type. If it is linear in gradient type, or any convective type terms gets cancelled. So now if you use that and then the global equilibrium, I find that this contribution does not change. This does not give you any contribution for each field, but this gives you a contribution for the energy field. You get a contribution, which is the some correlation. But here you don't get any contribution. Those are either in higher order or in Laplacian order. Laplace, if it is already in the Laplacian order, then if I take another derivative, because when you put it in the continuity equation, you get another derivative that will not contribute to the leading order of the current. Okay, so I'll just neglect all those terms. So now this is in this form. Now this quantity is current correlation, where this is the actual current, and this is the global equilibrium. I can find out this current, and this global equilibrium is actually H square, H minus tau. It's a Gaussian. So Gaussian term. No, this is I said no. This becomes, if I put it, it becomes correlations. This integral, I'm writing this explicitly here.
What is J? Early J or T?
No, if I put this quantities explicitly from this terms, this is the equation. I put it here, and then write down phi minus phi LE and simplify. I get these terms. And in this simplification, what I'm trying to
find, but
no, this is a slightly different.
No, current. It's a current.
It's a current, but it's only the nonlinear part in deviations.
Non-linear deep current.
Nonlinear in deviations.
Current.
And the other part, either you get nonlinear in deviations or you get a gradient type terms in the linear order. You don't get any convective term. Because any convective term in such a correlation will produce a diffusion term. And that already is included here. Okay, so you don't get. Okay. Those, because of by taking this thing it get cancelled. It has to cancel because it is already taken here. Yes.
So I'm saying that maybe it's just I think I'm confused. When you said you don't get a convective term,
No, I think
actually in this system, I understand why you said it mathematical, but actually in this system, if I start with the tiny perturbation, local perturbation, it still moves.
those are
Statistically, right?
those are here.
Velocities are still there.
Yeah, it's already here.
That is already there. So that is why you don't.
I already there, but I'm saying since I have taken in the deviation, it already got cancelled. In the formulation, it already got cancelled because of this term. So I'm saying this nice cancellation happens that you don't have the convective part appearing, only the nonlinear in deviation part appearing here. That automatically happens. That's what I'm saying in this formulation. And you see this nice cancellation, the factors in such way, they cancel in such a way that this becomes a gradient term. And all the previous order linear order terms for this energy part get cancelled only or remains only this part. Now, if you put it in this expression of the current here and do this calculation, then you see that this term doesn't give any contribution for the each field. It's just in the next lower order. Only the sensible contribution is this, where this quantity is like the correlation. You see this sum structure. There is this sum. You also have the sum. I just write down this integration inside the sum. Write it in this form. This should be dependent on I and N because there is Ji and this is Jn. Right?
How does it differ?
Yes, it will come. So this is the correlation. Now you have to compute this correlation, and if you write down this correlation, this global equilibrium, the deviations are in Gaussian distribution because I have shown you that the invariant measure is Gaussian in H. So H tilde is the deviation. So basically, in terms of this, it is in this form. For other terms, got zero, become zero because of the Gaussian. Okay. Sorry. Oh, 5 minutes. Okay. Okay. So now there is another point that I want to mention. is that this expression, even though I have written formally, it actually can argue that this actually should be independent of I and L for any finite system. If you do, if the system size finite and take t going to infinity, then this should become I and L independent. That is an argue. I am not going into the details, but if you want, I can.
System size.
If the system is fixed and take t goes to infinity, this t, there was a t there, no, already. Sorry, there was this t. I have already taken this t to infinity, assuming that this thing time is actually much larger than the time at which we have started. It's already I'm looking at a larger time scale. So that time scale I am considering to infinity because any error will be in the next step. But I'm saying you cannot do that. If you do it, this becomes I and L independent. If it is I and L independent, if it comes out, then it just becomes the boundary difference of the temperature. It doesn't give anything.
So what is aim?
So this is the correlation.
Capital N. Limit N can
N is the system size. So the only meaningful is that you have to take this N notation first, and then tau will be equal. So that means you have to first go to the hydrodynamic description and then complete this correlation, and then perform this integration. That means you have to make first the number of digits of freedom infinite first, and then take this, perform this integral and take this limit. That's the
opposite.
so then you'll get this will be independent of I and L. That's an argument I can tell you, but later I can show you. So you cannot, if you take the opposite, then it will become independent of I and L, becomes constant, it comes out and it becomes just a beta N and beta R.
I mean, does it convert or not convert?
What?
That limit, does this limit exist?
Yeah.
If you reverse the order, does this limit exist? So I think in
No,
this order it is finite, right?
reverse order is obviously it exists.
No, not so.
For a finite N largely it will exist. Finite.
Okay, maybe we discuss later.
It will exist. I mean, you can. So I can tell you that it will. You can relate this thing to a fluctuation of the total energy in a box of size I minus L, and that such fluctuation cannot go with it, so it cannot have a. Yeah, I can argue. But in this limit, it can actually have a different limit in this order. It can have a different expression, and it can depend on I and L. Okay, so very good. Now the question is, how do we compute this? So to compute this, it's a correlation of these fields, which are stochastic deviation fields. So you can there actually have to invoke the fluctuating hydrodynamics, and for this particular problem is very simple. It just depends only one field. So you can write down this fluctuating hydrodynamics. I do not have time to justify how do you write down this fluctuating hydrodynamics, but you can think of that you have this exchanges, but you are writing the evolution on a time scale is much larger than this. So such a time scale you have many exchanges, and you can invoke a central limit theorem by and then you can argue that this term will be a Gaussian term. So there is some argument by which I can actually argue, but I want to make a remark that this is actually same as this term, this equation. But in our it turns out that in our model you do not have this, and it does the only relevant field is this. Okay, but this is in the same form. I mean, you can actually get this equation phenomenologically starting from NFHD around like this also. Okay, very good. Actually, this is the identification. The first field is H, second field is E. These are the normal fields, and you can write down this formulation, and you can actually get this. Okay, very good. But what is the formal solution of this equation? So, formal solution of this equation you can write down in this form where this is the Green's function, and the Green's function satisfies this equation, of course. Now, what is the solution of this Green's function? Note that this Green's function is actually a Fokker-Planck equation of a random walker on an infinite line with this velocity and diffusion constant. This is not true. This was gamma. Sorry. So this is a random Fokker-Planck equation of a random walker. So the solution should be in this form where it's a drifted Gaussian. Drifted diffusion. So you have a drift, and this is the form. Okay. So now in this limit, if I use this solution with this form here and simplify, you get this integral. These are Gaussians, but integral over t. So if you perform this integral, you get a if you have done this thing over a finite size, you would not have gotten this. You have to take the n1 limit first and then take this. You have to do this in limit, otherwise you will not get. So you see that it actually becomes I and L independent. Very good. So you have an expression for this. You have these expressions. So we have this updated hydrodynamic equation. You see that earlier only with the local equilibrium approximation we had diffusive hydrodynamics. But once we consider the deviation, you get an extra term for the E field or corresponding to the beta field. You get an extra term. This field did not change, but this equation got changed. Earlier it didn't have such term. Okay, very good. But this is all linear order hydrodynamics. It's linear but non-local. Okay, now continual limit. So to get a sensible looking hydrodynamic equation, you would like to take continual limits. And as I have said that I have assumed that a slowly varying over space and time and the local equilibrium picture is evolving. So I would assume that the beta and tau fields are of this form where these are functions of these variables. Epsilon inverse and epsilon bar inverse are microscopic. This is length scale and this is time scales measured in microscopic units. Okay, the many multiples of microscopic length unit to line spacing, or let's say many multiples of microscopic time unit, which is k naught inverse or gamma inverse. And these are smooth functions. So I do this transformation. If I do this transformation, of course, for this field, it is very clear that it will have a ballistic term plus a diffusion term. So I should have a scaling function of this form. If I use such a scaling function, I get this kind of equation. And if I assume this scaling, this is the scaling of the length scale, this is scaling of the time scale. So I should have a relation. You know, depending on the relation, you get an equation. If I choose this, I get a diffusion equation. Okay, this is very simple. For the temperature field, I can do the same thing, and I get these terms. Very good. And another thing, under this scaling transformation, and if I take the epsilon going to zero limit, this function becomes basically this function. So you have a kernel here, and we have this epsilon and epsilon bar. And this is the scaling from the diffusion term. This is the scaling from the super diffusive term. Now, what kind of scaling you want to choose? Suppose I choose ballistic space-time scaling. That means epsilon bar is epsilon by v naught or something. Yeah, actually, I did not put the v naught, but assume that v naught is 1. So let's say epsilon bar is epsilon. Epsilon is a space scale. Epsilon bar is time scale. If you do this, then you will have epsilon or square root epsilon. So that means in epsilon going to zero limit, the temperature field doesn't differ. So that means if you look at different time, and correspondingly, if you go to that length scale, there you will see the temperature field did not actually evolve.
Hyperbolic scale.
This is hyperbolic. That means you have to if you choose this scaling, which is not that, then you see that this term becomes epsilon independent, something sensible, and you have a square root epsilon. This is a diffusive correction to that. So actually, this equation was obtained in a mathematics paper by Cedric and Patricia and Milton. Yeah, I don't actually understand their derivation, but this derivation, what I presented is a bit not so rigorous, but it's a bit more intuitive in that sense.
Yeah, so when epsilon tending to 0, I mean, it's a very large length, so the hyperbolic scale that's surviving.
No, it depends on
the diffusion will give only the leading direction, but not the plane.
But depends on as your what scale your time. If you scale your space accordingly, then you see something.
Is there a soft solution?
No, this doesn't have a soft solution because you have a diffusion term. Any non-zero diffusion term, however,
but if it
however small,
goes to 0, it goes to 0.
Yeah, equal to 0 and goes to 0 is different. That is how we cannot create a soft.
So goes to 0 and create a soft.
Equal to 0 and goes to 0 is different. That's different.
How? I mean, in this way, I mean, the equation we have written, tending to 0 is 0.
In this way, it is 0. In this equation, it is 0. But if you put
soft will be rounded off, but there will be a soft.
No, I'm saying it will not have a discontinuous derivative. That's what I'm going to say.
But epsilon tending to 0, the derivative is not the same.
No, epsilon equal to 0, the derivative will be discontinuous.
No, but epsilon tending to 0 is also same.
No, it is not same. Epsilon. No, and by the way, if you do not have this term, this equation doesn't have any sort. This equation doesn't have any sort anyway. This equation, Linear doesn't have any solve. So this question I don't know. But even if you have some other type of equation, this is a linear equation. It will not have any solve. First in beta. Yeah. But if you have a nonlinear equation, it might have a solve. But any equation term, if however small it is, it will not create into lambda. However small it is. So that you can actually there is a review by Jeremy Wade, and there is a very nice discussion. You can recast this equation as a Fokker plug equation of some Brownian motion, where you have a Brownian, this term becomes a diffusion term, so you have e to the minus I 1 by 4 d and d going to 0. The d going to 0 limit and d equal to 0 limit is different. The d going to 0 limit, you will actually select only the saddle point path, but d equal to 0 is not that, it is not selecting that, it's different. Okay, so so the mechanism is slightly different.
So the main solving it is non-local equation. That's
yeah, it's non-local but linear equation. Okay, so now if you do this super diffusive scaling, you get this term, but you can rewrite this equation in this form. And if you write down in this form, you have an epsilon c. Epsilon is actually length inverse. So you can actually interpret this equation in this form, that if you start with a peak, it will evolve, but as this thing, this spreading is smaller than epsilon c, it will this spreading will be dominated by this diffusion term. We'll have a diffusive scaling, and as this spreading becomes larger than this epsilon c inverse, it will be dominated by this. So we have an anomalous scaling. So, since I do not have a time, I cannot demonstrate this. So you can actually do the same thing for open system setup. You exactly do the same thing. But only thing is that the Green's function will have a different behavior. But finally, it also has a similar scaling, exactly same scaling, and you have exactly the same term for the equation for the temperature profile, or you have 1 over n. And this, you can find out that steady state current, and you can show the steady state current exactly has again 1 over square root anomalous term and a diffusive term as in the previous model, which you can write in this form by nc by n, where nc, you have an nc term, nc, I don't know, did I write? I didn't write, forgot. Anyway, there is an nc term. Nc depends on basically gamma and k naught, is the system parameters. But and a constant. So this is, it's very difficult to actually demonstrate crossover from diffusive to numerically to anomalous for a particular choice of parameters, because for example, if I choose some parameter where nc is 1, you don't see the diffusion, because diffusion is actually below 1, where you don't have any hydrodynamics. So here I see the scaling 0.5 minus 0.5, which is anomalous scaling, where nc is very large. That means you only have diffusive, where I see diffusive scaling, and I tried to choose a NC which is in between. So here actually it did not actually reach the final 1 over n. It was trying to go, and then it got affected by the anomalous terms, and it got changed. So it was trying to go there, but so that means you have to have a NC very large so that this exponent reaches 1, and then it goes to 0.5. But that is very difficult to demonstrate. So anyway, I think I have taken a lot of time. So yeah, this is the conclusion. We have looked at the anomalous transport in this model, and we have found super diffusive resolution, and that and with the correction to diffusion term, and that allows us to demonstrate a crossover from diffusive to anomalous transport. And I hope this derivation actually also try to reveal some of the approximation that goes into the derivation of thermodynamics. Yeah, thank you.
Studying the formalism of any system, there was a Hamiltonian description. Is Hamiltonian description necessary for the applicability of any system or any dynamical system?
You can do that. Right? As long as you have all these ideas of local equilibrium. So if you have a dynamical system where you have an invariant measure, which is your global equilibrium. You have such behavior, and then you have locally conserved quantities which have local conservation equations. This structure, and so that you have a possibility to make an adoption of local thermal. As long as you have that, you can apply it. So basically, you should have this kind of continuity equation. So is that? Yeah, this kind of continuity equations and the invariant measure somehow. It should be. You should have that. Yeah.
Is there any Einstein view?
Huh?
Einstein view.
Yeah, this MIL are like the transport coefficients.
No, Einstein view. They satisfy some diffusivity and mobility.
Of course, the noise terms, this actually in the fluctuating equation, these noise terms, they satisfy fluctuation distribution relation. But in general, they should definitely.
No, noise term. I mean, you have shown that they satisfy fluctuation distribution.
Of course, they can. I said usually it is written added phenomenologically by assuming D and B satisfies fluctuation distribution. But in this model, you can actually derive this term independently. They show that this and this satisfy fluctuation. For this particular model, so there are few models for which you can actually derive these terms. For where is this paper by Obisek, Shinichi Sasa and KG, they derived it for general Hamiltonian systems, and there the fluctuation distribution also appears, but it's a very complicated expressions. But the idea, yeah, okay, if you want, I can explain what is the idea.
So, after the thing, we add the non-linear of the taking into account another.
I mean, if you do not have this nonlinear term, then you will have a diffusion.
No anomalies.
If you do not have nonlinear term, you will have diffusion. But if you know that this system has anomalous behavior, then the only way possibility is to have a nonlinear term. What adding nonlinear term may not always give you anomalous, because then in the mode coloring theory, those coefficients, those strain age, has to satisfy some properties.
It's just like those two things, like fluctuation and dissipation. D and maybe H. D plus more.
B and B.
They satisfy a fluctuation dissipation. So similarly, this mode coupling H is also could satisfy some other.
No, they satisfy some relations so that the effective fluctuating hydrodynamics actually is consistent with the invariant pressure. Okay, they should satisfy. Even the actual efficiency doesn't have that satisfied, still it is applicable with some time and for large systems. Not a problem. But theoretically speaking, they should satisfy some relations. Second is that once you do the word coupling calculations, then there is this, you do transformations, there are these G matrices, and they should satisfy some properties. Once you have satisfied these properties, then you find out whether the mode coupling contribution is larger or not. They are dominating the. For example, let you beta change actually then Prakshina says that it is transport. Numerically don't see. So it's not that always it's applicable everywhere, but it's applicable to many. Of course, it also is based on many approximations. Right? It is based on the fact that the modes get separated and then it actually the normal modes, the correlation between diagonal, all these are approximations at many parameters get violated. Right? Then those scaling solutions may not be the actual solution of those mode coupling equations. Or these predictions are based on all those assumptions.
So you captured that anomalous transfer by using by adding a nonlinear term. So if instead, I mean, so that the evolution equation is not right. So time evolution equation is not. Sorry. I'm saying that we captured that anomalous transport by adding a nonlinear term by no.
But in this, the power plant equation, the linear response calculation that I have presented, then it automatically appears. That's the term that appears into the equation. Yeah.
I'm saying that
Theoretically, yeah.
yeah. So that the evolution equation is nonlinear. So I'm saying that instead of adding one extra term, can one think of it in this way that the transport coefficient is somehow dependent on the field variation, so that evolution equation is one.
It can be.
So that
It can be non-linear, but if you make the drive very small around this thing, you can make those to be finite values. Those transport coefficients. For example, it's a kappa. Kappa depends on temperature. It's a local temperature. But suppose you drive it by TL and PR, and TL minus TL is very small. So kappa at any temperature can be replaced by kappa of T naught. The very small drive, you will still have diffusive transport. Even though temperature can be nonlinear, but I think if you make the drive very small, you can get diffusive transport. But in this case, you cannot.
But if in the opposite, the temperature difference
Yeah,
is
so,
large,
so I'm saying,
then it is
yeah, you can get nonlinear, but that's not different from a normal transport. Just because the transport coefficient depends on temperature, you are out of the linear response regime. That's why you are getting nonlinear term. You are out of the linear response regime means you are in the nonlinear response regime. That's why you are getting nonlinear. It is not because of the fact that it's not diffusive.
this is very different for small delta.
Yes, very small delta T also. For anomalous case, you still get a non-linear profile. Even in the linear response regime, that's what I'm saying. Even in the linear response regime, we get nonlinear because of this non-local terms.
So physically, how do they be drift term? There will be some asymmetry in exchange processes.
Which drift term?
This H square or something.
No, that because it's there in the model automatically.
But I think the exchange are symmetric. I mean,
No,
there is
exchange
no
was symmetric.
momentum like variation, right?
Exchange was symmetric, but this is asymmetric.
I see. That is the time.
Yeah, for this model, this is asymmetric. You have a drift in this way. For other models, if you do not have asymmetry, then you have drift this way.
You have this term. So that creates that.
Okay, maybe we can continue on.